Hi everyone. So in this video we will discuss analytic continuation, in particular analytic continuation from imaginary chemical potential as one of the possibilities to sort of circumvent the sign problem and try to say something about what happens at non-zero real but small baryon chemical potentials in the phase diagram in particular of QCD in the temperature versus chemical potential, baryon chemical potential plane. We will, in the course of this class, discover that actually QCD at imaginary baryon chemical potential has a very, very intricate structure, which is rather interesting to study on its own, and that can also help us gain some insight both with respect to what is happening at zero chemical potential in terms of the mass dependence of the order of the thermal phase transition, and in terms of analytic continuation at real non-zero baryon chemical potential. So this is our first baryon dense, in a sense, application. And yeah, it works in the following way. That first of all, you are able to simulate and employ standard Monte Carlo techniques because the determinant of the fermion matrix is real, and in this case, you can simulate it for I mu I when mu I is a real number. And then you can do analytic continuation, in particular when it comes to evaluating the critical temperature or pseudo-critical temperature, which is an even function of the quark chemical potential, and that can therefore be obtained from direct simulations for all values of mu q square smaller than 0, so for imaginary values of mu q. And then it can be analytically continued according to this mapping of mu I square into minus mu q square to real values of mu q. So it really works in practice like represented in this sketch, that you can map out the phase boundary in this half plane where lattice simulations are doable, because this is the negative half plane for mu square in this case over t square in this sketch. And this you do by direct Monte Carlo simulations, that you collect this set of points that corresponds to the transition temperature. And then one can obtain the corresponding values in the other half plane when one has real chemical potentials by fitting the results that have been obtained in the other half plane and then extrapolating. Of course, there are systematic uncertainties to be taken into account because we don't have a clear ansatz for how should this function be fitted, and different functions can lead to different results. And this is precisely the kind of systematic errors analysis that was realized in this paper that you can see if you click on the link, where basically different ansatz were used, and they led to bands which were becoming larger as soon as the chemical potential was made real and large, while you have sets of simulations which are the red marks at negative values of mu b over t square. But as I said in the introduction to the video, the phase structure at non-zero and imaginary values of the chemical potential is pretty rich. And this is due to the fact that the partition function of QCD with, for example, one fermionic flavor and mu I different from 0 has or fulfills an extended center symmetry. What I mean by that is that this equality holds in which you have that the partition function is invariant under a combination of a shift in the imaginary chemical potential, which is what changes from the two sides of the equality in parentheses, and a Z3 transformation, which is the reason why you have a prime on the partition function on the right-hand side, which is defined in the continuum in order to change the fermionic fields in this way and the bosonic fields according to this formula. Note that the gauge transformation is realized by means of a matrix that belongs to SU3, and with tau in 0 to beta, this fulfills these non-trivial boundary conditions, which should not be new to you because this is basically the way we introduced the center symmetry in the first place. The same way you will be able to recognize that this 3 stands for the number of colors, so the formula I wrote strictly holds only for SU3. What this property of the partition function gives is periodicity in the phase diagram structure at imaginary chemical potential, in particular with a period which is 2 pi t over 3. That's not it, because we also have charge conjugation symmetry. In particular, again, in the same setup, we have that the partition function at mu I is equal to the transformed partition function when you swap the sign, when you change the sign of the chemical potential. That is to say, the partition function is invariant under a combination of a sign change in the imaginary chemical potential along with a charge conjugation transformation, which is defined in this way, and that acts on the spinors and gauge fields in the way I am writing down in the slides. What this gives us is, at the level of the phase structure of the phase diagram, is reflection symmetry around the mu equals 0 axis. So the phase structure really looks like in the plot I now have on the slide, and this is the Roberts-Weiss phase diagram, where what you can read is that you basically have Polyakov loop expectation values that depend on the value of the chemical potential at high temperature in the way which I am describing in this set of bullets. We know that as soon as there is a finite quark mass and we have dynamical fermions in the simulation, center symmetry is explicitly broken. The breaking parameter is the inverse quark mass, and in particular at mu equals 0, the real sector for the Polyakov loop is chosen out of this breaking. And what is happening in this phase diagram is that depending on the value of mu, the other two sectors are chosen as well. In particular, you have one, or the real sector, for mu I in the range that goes from 0 to pi 3, and then you have the other sector for pi 3 to pi, and then basically that's it, because periodicity and reflection symmetry can tell you exactly what is happening at other values of the chemical potential. So speaking of Polyakov loop expectation values at high T, the situation is like I just described. And then if one wants to know what is the expectation value for the Polyakov loop at low temperature, one can work by expressing the Polyakov loop in terms of a modulus and a phase, and then define the so-called modified Polyakov loop phase, which is defined in this way, that you subtract to the phase, this should have been mu I, but with a Greek mu, sorry about the typo, divided by t. And then this is the kind of observable that would be 0 at all mu I, and by that it would signal that you are below the critical temperature, which is in this case called critical Roberts-Weiss temperature, where you have one specific Polyakov loop selected, as long as you are within the ranges, and phase boundaries which separate the different ranges of chemical potential, which leads me to the next point, which are these Roberts-Weiss transitions that happen at pi over 3, at pi, and if you continue at 5 pi over 3, and so on and so forth. The order parameter is the modified L phase, at least the one that tells you where are you with respect to this temperature. However, the peculiarity here is that every beta and every temperature is critical along this boundary. And the only thing that changes from low temperatures to high temperatures is that the nature of the transition changes. You have a crossover at low temperature, and you have first order phase transitions at high temperatures. This was really worked out in the paper by Roberts and Weiss. They used different approaches for the T to infinity limit and for the T to zero limit in order to work out that there are first order phase transitions at high T and just crossovers at low T. Okay, without entering much more into detail, the point I'm trying to make is that you have one parameter more, which is mu I. You have some extended center symmetry. I'm calling it more symmetry, but this is also broken at high temperature in the way that I just described. And it is basically the result of the interplay between the chemical potential and the Z3 symmetry summarized in these symmetries of the partition function and in the way that the Polyakov loop behaves with respect to these symmetries. So all in, we have a very non-trivial phase structure. So while, as I said, as soon as you have finite dynamical quirks, dynamical quarks with finite masses, you are breaking Z3 symmetry explicitly. You still have center sum transformations that can be undone by a shift in mu I, and at high temperature, your average value of the Polyakov loop is cycling through the three sectors. And another important point is that the thermal phase transition, which basically continues from the first order Roberts-Weiss line through this black dot, which is commonly referred to as the Roberts-Weiss endpoint, and then continues towards mu equals 0, it also extends to real positive values of the quark chemical potential. What you should do if you want to study this phase diagram is you need to adopt the techniques that are analogous to what we studied together for day one and in the assignment of day one. But the fact that every beta is critical if you are, for example, simulating exactly on this line makes the analysis a little bit more complicated than the way to find out the location of the endpoint is by looking at the crossing values of the kurtosis of the distribution at different values of n sigma. And which distribution you look at depends on what Roberts-Weiss line you are sitting on top of. For example, if you are sitting here, it is enough to look at the imaginary part of the chemical potential, and that is sort of telling you which sectors you are populating and when is the population of the two sectors becoming symmetric, when do you have a two-phase structure pointing towards a first-order phase transition, and when at low temperatures you just have a crossover. If in the setup in which you keep mu I fixed and you just change the temperature. So it is really scans that are happening along the Roberts-Weiss lines, those kind of analyses that I'm talking about. And then what can happen? There are several possibilities for the order of the Roberts-Weiss phase transition in correspondence to this black dot, which I call the Roberts-Weiss endpoint. One possibility is that the first order line just terminates into a second order critical endpoint precisely at the endpoint. However, it can be that our first order transition is still strong enough such that the endpoint is actually a first order triple point made triple by the fact that there is coexistence of three phases at that point. And then there are first order lines that extend farther away from the critical value of the imaginary chemical potential for the Roberts-Weiss phase transition. And then at some point along the line, you can have a second order critical endpoint. This point can be anywhere. It can also basically cross the vertical axis, the temperature axis. And there is a third possibility. The third possibility is something in between, specifically that this endpoint becomes a so-called tricritical endpoint. So how comes that there are so many possibilities, and are these really all realized, is the relevant question. And the answer is that yes, they are all realized in QCD if you are sitting on the Roberts-Weiss line. And what makes the system change from one behavior to another is the value of the pair quark masses that you have given in input to your simulation. So if you want, you can think of it in a three-dimensional view, and basically you would have for different masses a sequence of triple points that would end into a tricritical point, and afterwards you would just have second-order critical endpoint, which is precisely the kind of picture I'm showing to you here. This will remind you of another plot you have seen already. This is the Columbia plot at Roberts-Weiss. So instead of displaying the order of the thermal phase transition in QCD as a function of the bare, light, degenerate, and strange quark masses at mu equals 0, here you're doing exactly the same thing, but at a critical value of mu in the Roberts-Weiss setup. And then you can identify for what bare quark masses you have a tricritical phase transition at the endpoint, because all points in this plot are endpoints, okay? And then they can be first triple, and then you can change your mass setup, and you have a Z2 transition until you locate the tricritical boundary, analogously to what we can do when studying the dependence of the order of the phase transition in the standard Columbia plot. But now we realize that the two plots can be superimposed in the following way, that you have the ordinary Columbia plot on top, and then at the bottom, at the critical value of the imaginary chemical potential for Roberts-Weiss, in this case, the axis is mu over T all squared. So at the bottom, you have this other plot. And then you can simply draw surfaces that connect one plot to the other, okay? And this is what is done in this three-dimensional plot. And this is done assuming that the first order scenario is realized for the ordinary Columbia plot, which means that you have a first order region that extends all the way up. And even in the two flavor theory, you still have some finite width first order region. Why is that interesting? Because it helps us telling something about what's happening at mu equals 0 due to the following consideration. One can, and it turns out to be easier down here than up there, locate the tricritical point. Why is that easier? Just because the extension or how wide the first order triple region is with respect to the first order region at mu equals 0. That is wider, and this is an empirical fact. There is no universality behind it. It was just simulated, and people have observed that this is the case. Then it can be significantly cheaper to simulate down here and to locate the position of this tricritical endpoint. And with that, what we can do is we can follow the Z2 line that stems out of that tricritical mass. And here I have basically this view with two different possibilities for what is happening at mu equals 0 and above. Mu over T squared equals 0 and above. This point, this red dot, the tricritical light mass, is precisely this red dot in the 3D plot. Then one can start from there and follow the Z2 line and go up. Going up also means going towards smaller and smaller masses. And what one knows is that at some point towards the chiral limit, there will be a tricritical value also for the chemical potential. Now, this can happen to be below or above mu equals 0. And this is already telling us whether we have a finite first order region up there or not, because here you would have it and here you would not. And yeah, then one can send mu I to 0 in simulations and map out these Z2 boundaries. The other advantage is that anytime there is a tricritical point, either here or there, but in particular the expression here is written for this tricritical point, then we know the way that the Z2 line bends into that tricritical point. Specifically, we know what are the critical exponents, and for tricritical points, these are basically the exponents that I am representing in the fit ansatz that I would use in order to extrapolate towards the chiral limit after having simulated far enough, that is, at low enough masses and at closer to 0 enough values of the chemical potential. This kind of studies have been done, and as I said, they are precious because they can sort of provide an answer to this question, whether you have a first or a second order phase transition in the chiral limit of the two flavor mass theory. Motivations, and this was referred to many times already. Why do you care about what is happening at masses which are not physical? Why do you care about what is happening at imaginary chemical potential? There is always this this way of reasoning that somehow these lines that we see at mu equals 0 or whatever it is happening at real mu, it all connects to what is happening at imaginary mu. And if there is something that like the enlargement of the first order region that makes it cheaper to explore, then it is reasonable to look at that with lattice simulations. And it is also, as I said, interesting to, it was interesting, and people have done it to confirm what Roberts and Weiss had obtained with their calculations in the high temperature and low temperature limits. So I would want to just finish by showing you some of these results that I mentioned. So for example, in the top half of this slide, I have results that relate to the to this Roberts-Weiss-Columbia plot, but more specifically to this tricritical point over here and a tricritical point at the height of the physical point in this direction. Yeah, this plot, which is taken from this paper over here, proves that there has been a lot of work invested in this. And unfortunately, what it also proves is that we don't have continuum extrapolated results yet, and there is a very strong dependence on many things. So the n tau, which is telling us how far away we are from the continuum limit, but also different fermion discretizations like Wilson or staggered, and within staggered, even improved and unimproved are providing very different results. So yeah, might be cheaper than at mu equals 0, but it is still a lot of work, and there are no continuum extrapolated results. So yeah, too bad. And then here below, I have results that instead have to do with basically changing the value of the imaginary chemical potential away from the critical value for Roberts-Weiss, which is represented in this plane and in the bottom plane in the three-dimensional plot, and going up. And this was also done on rather coarse lattices, I would say, back in 2014, with the result that at mu equals 0, you have a finite width first order region. And yeah, actually, this is the window in which it was possible to fit according to tricritical scaling exponents. And then people have looked also at what is happening analogously in strong coupling QCD as well as in 3D POTS model, where similar patterns are found. And yeah, in this case, the plot has the mass on the vertical axis and mu over t square on the y-axis, but don't be confused by that, because this is precisely the continuation of this line up in the other plot. And one could perform analytic continuation in this kind of setup, starting from simulations at imaginary mu. And this brings me to the summary. So we have discussed the Roberts-Weiss phase transition, and I have told you that the fact that the values, not the voles, the values of beta are critical complicates a bit the analysis. Nevertheless, there is the advantage that the first order triple region are wider than at mu equals 0, and this has led to many investigations. Even though whenever you switch on improvements, you only have upper bounds for what is happening at mu equals 0, and there are no continuum limit results available yet. So there is still work to do in that respect. But there is this fancy and interesting phase structure and these interesting symmetries of the partition function of the QCD, which depend on the fact that the potential is imaginary rather than real. And then I have discussed, so I closed the loop back to my first slide, how one does analytic continuation of the transition temperature to real values of the quark chemical potential. And I mentioned that a careful analysis of systematic errors is mandatory because there are several plausible fit ansatz. And yeah, when you do analytic continuation, you always have to bear in mind that the radius of convergence is given by the closest non-analyticity due to phase transitions. But yeah, something more about this will come in the coming videos. So that's it. Thanks for watching.